Hello everyone, welcome to our presentation. It's called Hunting and Exporting Recursive MMO Flows in QEMU and KVM. In this talk, we will share our security research on QEMU and KVM, a hypervisor widely used in cloud computing, and analyze the root cause and the common consequences of recursive MMIO, thus disclosing a new attack service. So, who we are? My name is Qiuhao, and now I am a graduate student at the Harbin Institute of Technology. Gaoning is a PhD candidate at Zhejiang University. Our research areas include system security and fault testing. This is the outline of our talk. I will try to finish it in 20 minutes so we can have some time for Q&A. First, let's give some backgrounds about QEMU and KVM. KVM is a Linux kernel module that makes Linux behave like Type 1 hypervisor. It can provide hardware-assisted virtualization to user space program. QEMU is an embedded program which provides virtualization of an entire machine to run guest OS. This figure illustrates the high-level architecture view of KVM with QEMU. The virtual machine and QEMU run in separate threads. With the help of KVM, the guest OS can execute most of its instructions directly on the host CPU. But when it tries privileged operations like port mapped I/O or memory mapped I/O, it will trap into KVM. The KVM will decide how to handle those VM exits. Most of the time, KVM will return to QEMU and tell it why the VM exit. QEMU will then emulate the corresponding devices. So what is recursive MMIO and what are the root causes? In QEMU, MMIO is emulated by intercepting the memory access, and the DMA is usually implemented by user space memory copy. Additionally, a virtual device can see and access memory regions of other devices, including the system RAM and the MM regions, since the guest OS can control the destination address of DMA. When it sets a destination to overlap with MMO regions, the relative I/O handlers will be called during the data transmission. However, when the write to MMO operation forms a loop, it will cause problems. The MMO handler triggered by the DMA may have side effects on the device that launched the DMA. So when the control flow returns to the device, bad things may happen. For example, as shown in the figure, we set device A's DMA destination to its own reset register. When it writes to the register later, its internal data structure will be freed. After the reset routine returns, since the I/O has not been completed, the freed data structure will be used, thus triggering a UEF exception. This phenomenon occurs as long as it forms a recursion. For example, we can also create an indirect recursion. Device A calls the MMO handler of device B through DMA, triggers the DMA operation of B, and B will then trigger the MMO handler of A. From a big picture, the incomplete isolation between DMA and MMIO is the underlying cause of recursive MMO flows. Different CPU-to-device communication methods, such as MMIO and PMIO, should not affect the DMA, because by definition, DMA is a memory-to-device communication method that bypasses the CPU. So in essence, recursive MMO flows violate the constancy of device state-machine transition. Therefore, depending on the design and the implementation of different devices, the harm is also different. We give 3 common consequences here. The most harmful possible vulnerability is the use after free, and it's usually caused by a pattern: write to MMO reset register, free device internal data, use freed data. If an attacker can occupy the released data between free and use, it's possible to escape the virtual machine. In some devices, structures like data transfer size and data index are stored in the device's global buffer, and this data can only checked before being used. So attackers can launch DMA to the MMO register that can modify this data. Then an out-of-bounds access situation will happen later. Attackers may achieve information leakage or control flow hijacking. Finally, the device may launch DMA to the MMIO register that will trigger the same DMA action, thus forming an endless recursive call. Attackers can use this flow to crash the hypervisor. Besides QEMU, we did some experiments on the Oracle VirtualBox, and it seems also affected. We believe that similar results can be achieved inside the guest OS. We leave it as a future work to research VirtualBox and other hypervisors. You can read our white paper for more details. Next, we will explain how to make the hunting and the exploitation process automatic with CodeQL. There are two common paths to trigger the recursive MMIO, from an MMIO handler to another MMIO handler, or from a bottom half or timer callback to an MMIO handler. To automatically find those paths in virtual devices with CodeQL, we first need to describe the characteristic of the MMIO handlers and BH timer callbacks. As for the MMIO handlers, it's defined in struct memory region ops. So we can search each device's memory region ops object and get the MMIO handlers. Here we omit the MMIO read handlers since most of them cannot trigger DMA. For bottom halves and timers, they are created by calling QEMU BH new for and timer new ns, and the callbacks are passed as the first and the second parameters, so we can search those two functions in each device to get the BH and timers callback. The last functions we need to know are the write to physical address APIs, which implement DMA. According to QEMU's documentation, there are a lot of such functions, like DMA memory write, PCI DMA write, DMA buffer read, etc. Actually, they all call to address space write in the end. So we can just search those functions for write to physical address gadgets. To improve the performance when searching, we hard-code those functions in CodeQL queries. Then we can use the path graph module in CodeQL to find all the possible recursive paths. We need to define our own LGS query predicate, which is the core relationship, and the nodes, which is arbitrary functions. Finally, we can leverage the transitive disclosures in CodeQL to do the search. For example, there is a path from MMIO handler to PCI DMA write in the MegaRead device. We said there are three common consequences caused by recursive MMIO flows: user after free, out of bounds access, and endless calling. Since UF is usually easier to exploit, we only focus on this kind of vulnerability here. To find all the possible UF flows, we need to know the possible path from an MMIO write handler to a reset function call. Similar to previous queries, we can use CodeQL to do this quickly. For example, we can find a path from an MMIO write handler to a reset function in the EHCI controller. Now we know three types of paths: from MMIO handler to DMA write, from BH timer callback to DMA write, and from MMIO write handler to device reset function. To find devices which may have UF flows caused by direct recursive MMIO, we can calculate the intersections of those paths manually. For example, if there are type 1 and type 3 paths in device A, then device A may have UF flows. To explore the UF vulnerabilities, we have to find the malloc primitives which can occupy the freed chunk before it's used. There are two possible ways. First, after the control flow returns from the MMIO reset handler, a malloc that allocates chunks the same size as the freed chunk will be called. However, after some reviews, we think it's hard to find such primitives in vulnerable devices. Second, instead of calling malloc in the same device, we can write to another device's MMO region in which a chunk will be allocated. Then we return to the vulnerable device to use the freed but occupied chunk. Since scat-gather DMA is common, it's easy to find vulnerable devices that perform multiple DMA write operations. So we choose this method. So our new goal is to find a malloc that can be triggered by an MMO write, and the guest can control the content of the allocated chunk. It's best that the size of this chunk is also be controlled. Based on past experience, we guess this primitive has the following characteristics. First, there should be a free from the allocate call. Otherwise, the guest can keep allocating chunks and crash the hypervisor. Two data structures are usually used for data transfer between guest and host: linked list and array list. To get size-controlled chunks, we focus on arrays which are composed of multiple constant size units. Third, there should be a read from guest action after the malloc call, so we can control the content of the allocated chunk. Last, the parameter of free, read from guest, and the return value of malloc should be the same pointer. Then we can find the multiple free malloc pairs. Here we discuss a primitive in the Intel HDA device. This free malloc pair is in the function that gets the buffer descriptor list from the guest OS. The guest OS can write arbitrary content to the list. This routine is triggered by setting the run bit in HDA's stream control registers. Moreover, the LVI variable is also controlled by the guest, so by calling this routine, the guest can allocate any chunk size multiple of 60 bytes. Finally, there are 8 streams in the HDA device, which means the guest can call several free and allocated primitives in one scat-gather DMA operation. So this is also a perfect primitive to construct the heap function. Using the CodeQL queries, we found multiple bugs. Here we will share 2 exploitable vulnerabilities. The first one is a UF vulnerability. In the NVMe device, DMA functions can be called without check if the destination region is overlapped with the device's MMO region, which results in recursive MMIO. What makes this flow easy to exploit is after the reset finished, the NVMe enqueue rec completion will be called, in which CQ's timer is set to fire 500 nanoseconds later. However, the timer is freed in the reset routine. Since there is a callback pointer in the timer, the guest can hijack RIP directly if he can occupy the freed timer. The second one is a stack overflow bug in the NVMe device. We found it when reviewing the previous UF bug. It's not a recursive MMO flow, but can be helpful later. This function transfers device log to the guest OS. The guest OS controls variable off. If it's bigger than 4K, an integer underflow will happen, and the transline will be set to buffering, which is also partially controlled by the guest, thus leading to stack overflow. Even worse, since off can be set to any number greater than or equal to 4K, the PTR parameter of NVMe C2H can be set to arbitrary address, resulting in arbitrary memory read from the host to the guest. Last, the NS list buffer is used as the source data of DMA operations later, which can trigger the previous UF bug. So we can make the source data of the DMA operation from an arbitrary address, like the guest RAM we controlled. Leveraging these 2 vulnerabilities, now we will discuss how to exploit those bugs and demonstrate a VM escape in the end. As mentioned before, we got a recursive MMO flow triggered by DMA that calls UEF, and the freed structure contains a timer pointer. And we got an arbitrary memory read flow which can be used to bypass ASLR and leak the guest RAM address. Last, there is a powerful malloc primitive in the HDA device. So our plan is following. In the guest OS, we construct a fake timer and prepare a buffer for the MMO write operations later. By leveraging the arbitrary read flow, we can leak, By leveraging the arbitrary read flow, we can leak the address of system at PLT and the address of the guest RAM. Since the content of the MMO write operations in the UF flow is from the buffer of the arbitrary read flow, we make the source data of MMO write from the buffer we constructed in step 1. By leveraging those two flows, we launch scatter-gather DMA operations to NVMe MMO region. And the first MMO write is to trigger the malloc in HDA device, allocating 3 chunks the same size as the QEMU's timer, thus cleaning the T cache of the main thread. In the same DMA context, the second recursive MMO write is to the reset register of NVMe controller, releasing the CQ structure. In the same DMA context, the last MMO write is to trigger another malloc in the HDA device, thus occupying the freed CQ structure, and the timer pointer in CQ now points to the fake timer we constructed in step 1. When timer mode is called later, the callback in the fake timer will be called. Since we control the callback and its parameters, a control flow hijack can be achieved. Here we briefly give some explanations. You can view the white paper for more details. In QEMU, a memory region backed by host mapping memory will have a corresponding pointer in the heap. So if we can leak the address of the heap and search through it, we can get the guest RAM address. Luckily, after some reviews on the stack, we found a stable pointer that points to a variable in the heap, and its value is always below the guest RAM pointer. So instead of getting the base address of a heap, we can just search start from this pointer. The next problem is how to find the RAM's pointer on the heap. We observe that the virtual address of RAM is always aligned to 14 megabytes when we set the guest RAM size as 2 gigabytes. And there is a stable pointer on the stack that points to a mapped memory region whose high address is the same as the RAM's high address. Last, considering that only 48-bit addresses are available, we can design 3 patterns and search on the heap in units of 8 bytes. Finally, got the address of the guest RAM. The right figure shows the process to leak the RAM address. When we trigger recursive MMO flows in the NVMe device, the DMA source data is described by a structure called PRP. A PRP entry is a 64-bit memory physical address divided into 2 parts, page start address and page offset. There are 2 PRP registers. PRP1 points to a page, PRP2 points to a PRP list which contains a list of PRP entries. This figure illustrates the PRP structure we use. As we said, we should trigger 3 discrete MMO writes. So we need 3 PRP entries to clear the T cache, occupy the freed timer, and corrupt the timer with guest RAM content, thus executing arbitrary code on the host OS. The reason that we must clean the T cache is that we found if the current thread's T cache is full, the allocator will pull the free chunk back to the thread in which the chunk is allocated. This will prevent us from occupying the freed chunk. In this demonstration, we will make the timer's callback point to system at PLT and let the first parameter point to the norm calculator stream. So a calculator will pop out on the host. So how to fix those flows? There are 2 typical mitigations. The first mitigation is to add busy flags in every device. When we enter the MMIO or BH timer callback, the busy flag is set, and when the IO operation is completed, the busy flag is unset. If the busy flag is set when we enter the device, an error will be reported. The disadvantage is that we need to add code in different locations for different devices. The left part of this figure illustrates the design of this solution. The second mitigation is to put the checks on the bus. By analyzing the data destination address on the bus, the exercise that can generate a loop is prevented. However, now we need to record all the devices that can be accessed and release the records when it's over. The right part of this figure shows the design of this solution. The community adopted a hybrid solution which puts the checks on the bus and leaves the device to decide whether to load writing to a long run area. You can view the links for more information. Finally, would like to share some thoughts about bug hunting and open source security. First, this design flaw has a large impact and should be fixed as soon as possible. Second, this flaw existed in QEMU for at least 10 years, or more than 1 year just considering the large-scale appearance. For these bugs, all communication is public except the one we use to achieve VM escape. So if you are a malicious hacker, a fast way to attack an open source software might be checking its bug tracker instead of finding vulnerability by yourself. Last, when auditing the hypervisors, we should pay attention to the different behaviors between virtualization software and real hardware. We will release the white paper and the VM escape code on GitHub a week later. You can find a lot of details there. And that's all. Thanks for listening. I think we have some minutes for Q&A.